Here's our next video. It's on the conjugate pair theorem, which says let a polynomial whose coefficients are real numbers. Um, if a plus bi is a 0, which is a complex because it's imaginary right here, the complex conjugate a minus bi is also a 0. So remember, on the side I'm over here, I'm going to think about the quadratic formula: x equals opposite b minus the square root of the discriminant all over 2a. Remember, if this discriminant, the number under the square root, was negative, then I would have some result like -2 plus or minus the square root of -4 over, let's say, 6. And I would get the square root of -4, which would be 2i, and then I could divide everything by 2. And notice I still have that complex conjugate, that imaginary or complex solutions come in pairs. They're never just going to be a single. One example is the quadratic formula. Another example where we got them is just when we use the square root method. Maybe we had x squared plus 4, and we said, well, that's not a difference of squares. And we subtracted over the 4 and we square rooted it, and we got x is equal to plus or minus 2i that way. So either way, imaginary or complex solution comes in pairs, conjugate pairs. So that's not the case for reals. Just because if we get a 3 doesn't mean we always get a -3. There are scenarios when we do get a plus or minus 3, but that's not always the case. So when I'm looking at example 1 and I want to write the polynomial in standard form given the zeros, I want to think about two categories. I can have real zeros, which are my x-intercepts, and can have complex or imaginary. Complex, remember, has a real part and an I part. So on this one, it says given the polynomial has zeros 3, that's real. Remember, that just is going to be a standalone. It's not going to have pair up. But I have 2i, and because I know 2i is an imaginary solution, that it has its complex conjugate, which is minus 2i. Okay? And so now I know I have 3 solutions, so I'm going to be a cubic, and I'm going to write these in factored form. Okay? And now that I'm in factored form, I want to write the polynomial in standard form. So I highly suggest that you multiply first your complex by your complex. Don't mix your complex factors with your real factor, because you'll get a complicated solution. Because something's nice when we multiply conjugates of imaginary. Remember, conjugates are going to have the middles wash out. So I have x squared, and I know my middle here is going to cancel to 0, so I'm going to just go ahead and multiply my last, and I get -4, and then I squared, and then just remember I squared is -1, and so that just changes the sign to +4. And that's easy to tell. Like if I solve that for 0 again, just like the side example that I did, it would get you plus or minus 2i. And now that my complex solutions or factors have been multiplied together, now they look like regular old real factor, even though it's, no I left. Now I'm going to distribute through my real. So this one, these are not conjugates, so I'm going to need to multiply all 4 parts out. So I'm going to start with the x, and I'm going to multiply it into both of these. And I get x cubed, and then I get plus 4x. Then I'll move on to the -3, and I'll multiply the -3 into both parts. And I get -3x squared minus 12. And then all together, I'm going to get x cubed minus 3x squared plus 4x minus 12. I'll just call that x. And there's our polynomial in standard form. Like I said, we had 3 solutions, 1, 2, 3. So my leading term should be a cubic. Okay. The next one is another real and imaginary, these are actually complex. Okay, so my real 0 is -1. Don't forget, that doesn't mean positive one comes along. We can make that mistake sometimes because we're so used to pairing up. But since they give me 2 plus I know the conjugate, a complex solutions come in pairs. So I know 2 minus I. Remember when it's a binomial that the only thing that is changing is that middle sign. Notice when it was a monomial, the only thing that's changing is the sign of the I. Same thing here. The sign of the I is changing, not the sign of the real part, the 2. Okay, so now I'm ready to write these in factor form. X plus 1. And then because I have a binomial, that normal subtraction that I distribute to my monomial, which switches the sign, has to be held out. We'll take care of that in a second. So notice both of these are going to get the negative sign because the definition of when you write from a x-intercept or a 0 to factored form, the definition is x minus the root or the x-intercept. And that's why, like up here, my real was -1. So when I do x minus the root, which is -1, it switches the sign. And so that's easy to see, and then it's easy to solve those. So we have a really good idea of why those switch signs. However, when you get a binomial root or solution, right? This one would be a solution. It's a complex solution. But that negative is going to have to distribute through to both terms, not the monomial one term. So that's why for right now, I'm just holding the negative out in front of the binomial. Okay, and now what you want to do is, again, I'm going to want to multiply my complex solutions together because when we multiply them together, the i's are going to go away. Okay, but because it's a binomial, it's a little bit trickier. So there is a easy way to do these, but it takes a little practice. The first thing that you're going to do is you're going to distribute that negative through that I was telling you was being held by the parentheses of the binomial. So now I have -2 minus I. Now I'm going to distribute this negative through. I get x minus 2 plus I. I'm not going to worry about the x plus 1 until after I multiply these together. Now what we're going to do is we're going to call regrouping. So notice before my grouping symbols were around the 2 plus I and the 2 minus I. Now what I want to do is regroup those parentheses around the x minus 2. Now what you can notice is I have a conjugate pair here. If I called x minus 2a and I called the I b, then what I would have is the same two terms, right? X minus 2 and x minus 2, which is a, but they have opposite signs in between. What this does, it makes it easier. When I know I have conjugate pairs, I know my middles cancel out. And so my result is found by multiplying my firsts and my last. I don't have to worry about getting those complicated middles because we know that they're going to wash out or they're going to go to 0. Okay, so that's what I'm going to do. I'm going to multiply these two together, x minus 2, and this will always work out. And it's squared, but I know I'm going to have to multiply those together, so I'm going to keep it in expanded form. And now I'm going to multiply my last. So I get a negative times a positive, which is a negative. I times I is I squared. Okay. So now what I want to do is reduce this down to a polynomial with no I. So the first thing I'm going to do is distribute my x minus 2. So I get x squared minus 4x plus 4. And then I have this minus I squared. Remember, I squared is -1. And so then I have a -1 times that subtraction sign. So it becomes a positive. So now I have x squared minus 4x plus 4 times x plus 1. So you can tell when it is a binomial complex, 2 plus I, 2 minus I, it's a little bit more work than when they were monomial ones like the ones above. But either way, we're using the property of conjugates that we only have to multiply first and last when we do our imaginary in both scenarios. Okay, now I'm left with the distributive property. So I'm going to distribute my binomial into the trinomial. And I get x cubed minus 4x squared plus 5x. And now I'm going to go back and reset. And I'm going to take the positive 1 and I'm going to distribute. Let me get a better color that shows up. Positive 1. Woo! Maybe not that. Let me see. There we go. And I'm going to multiply the positive 1 into all three. So I get 1x squared, and I get negative 4x, and I get plus 5. Now all I just need to do is combine my like terms, and I have f of x equal to x cubed minus 3x squared plus x plus 5. And there is my cubic polynomial. Okay, the last example is what happens if I have all complex or imaginary solutions. So real, this one has none because I have I and 4 minus 3i. So my complex imaginary solutions, I have one imaginary solution, negative I. So I also know positive I goes along with it. And I have 4 minus 3i. So I also know 4 plus 3i. This is a good example of what sign changes when it's monomial versus a binomial. I'm going to group those together. Remember, I have to hold off that negative sign for these binomials. I'll distribute it in the next step. Okay, so when I multiply, I have multiple I factors. You still want to stay consistent and multiply the like ones together. So these were the ones that conjugated up together, and my other ones were these. So we don't want to like multiply one of the yellows with one of the reds, because then you're losing that nice complex conjugate, right? That makes this multiplication a lot quicker by multiplying first and last. I'm going to do the easy one first. And I know I squared is negative 1, but I have a subtraction sign, so this becomes a positive. Notice the monomial ones, these ones that are just I and negative I, are a lot easier to multiply together, not much work. However, the binomial ones require a little bit more multiplying and regrouping, those kind of things. So I'm going to distribute my negative in. Technically, if you get good at that at the very beginning, you could distribute your I in knowing that you're going to regroup. It's kind of up to you, but I'm going to go through the process of regrouping. So I distributed my negative in, and now I want to regroup and put my parentheses around everything, right, except for those i's. I'm kind of like isolating those by themselves. And I know I still have a conjugate if x minus 4 is a and 3i is b. Notice I have the same two first, x minus 4, and the same two last, which is 3i's. The only difference is separated by a plus and minus. So these are complex conjugates. It's good to recognize that because that enables my multiplication to become much easier. Because now I can multiply these first together, and I'll just keep them in expanded form because I'm going to want to multiply those two things together. And I'm going to multiply my last. So a positive times a negative is a negative 9, and I get an I squared. Now I'm going to go ahead and multiply these binomials together. I get x squared minus 8x plus 16. And I know this is I squared is really a negative 1. And it's going to multiply and change that to a positive 9. Combine my constant terms. Looks like I get a positive 25. I'm going to bring my binomial term down. And now I'm ready to distribute. So I'm going to start with my x squared, and I'm going to multiply it into all three terms. I had 4 solutions, right? 1, 2, 3, 4, so I should be a 4th degree polynomial. Once you notice I get a 4th degree right out the bat, and then plus 25 squared. The next I'm going to multiply is the second term in my binomial, my 1. I go through all pieces, and I get 1 times x squared is an x squared minus 8x. I'm just going to write these combined. I have an x to the 4th minus 8x cubed plus 26x squared minus 8x plus 20. And there's my polynomial. Okay, so there'll be some delta math on multiplying some complex together. And tomorrow is our last INB, and we'll start reviewing on Friday and all next week for our test the following week. Thanks.